So while I'm waiting for the last couple of people to log in, I'm sorry about the webcam thing today. Apparently, I have the brain cells of a gnat today. Um, I loaned my webcam to my daughter because she has a Saturday morning class. And since I was gone for part of the weekend, somehow I totally spaced and forgot to get it back from her when I went out the door this afternoon. Because on Tuesdays, I usually do this from my office down Hilltop. And so, yeah, I have no webcam because there's no webcam built into my computer. So I have an external that I usually use. So yeah, I've got the screen share capability and the whiteboard, obviously. I just don't have the webcam. So it'll be a little bit different, but not substantially different today. I'm missing 2 or 3 people, I think. So I kind of dawdle a little bit, waiting to see if they log in. I started grading tests. I graded a couple of them. I have not graded all of them yet. If I did grade, because of the way the system's set up, I think it should post to your account. If I have graded each of yours, yeah, when I grade it, it should post to your account. But I've got a few that I haven't finished yet. So like I said, last week, it usually takes me a day or two to crank through them. I will confess, I'm really used to grading papers, but grading them digitally kind of is excruciating because of the way you have to do it and the way Canvas prompts me, because obviously some of the test was like multiple choice and true false and that sort of stuff, but some of it was problems. And so when I log in, it provides me with this list of here are the ones that you must grade manually, but it does so for each student separately. So yeah, that kind of contributes to the excruciating part of grading it on Canvas. All right, let me find my file. We have not quite finished the tail end of kinetics. We have just a little bit left to go. So let me see if I can call this up. All right, the last bit that we had not gotten to, because I think the last thing we were talking about was the alternate version of how to figure out activation energy. And then we kind of get to catalysts, and we didn't really kind of get through all of that because I wasn't really going to push too hard to do it right before the test. All right, so back to the catalyst idea. So look at your graph here and the fact that when you have no catalyst, you have the much steeper hump in the middle of your graph, which implies that you must add a great deal more energy in order to get this reaction up to the top of the hump where the transition state occurs before you actually slide on down the other side and get your products. If you have the catalyst present, it's not that you get rid of the hump entirely. That's unlikely. I won't go so far as to say it's impossible. It just falls in the unlikely category. So in this case, your hump is much smaller. you have to only add a small amount of energy in order to kickstart it and kind of get it over to the other side there where the products occur. We want to talk a little bit about some of the different kinds of catalysts. Also, something we're going to mention that we'll come back to later is the rate, the fact that it goes faster, actually can be in either direction. You can either make a reaction go forward faster, you can also make it go backward faster, and this will eventually become relevant as we dig into the depths of equilibrium, which are the next chapter. And that gives us an idea of like, this is something we're going to see again. Catalysts are not strictly limited to this chapter. They also occur or are mentioned as part of some other chapters too. We're going to have three different kinds of catalysis. We've got the homogeneous, the heterogeneous, and the enzyme, which is more biochemistry and less general chemistry. So I went digging around looking for a couple of not bad images to kind of throw in with this to give you a little bit better idea. When we're talking about the homogeneous ones, homogeneous, like it means when we're talking about solutions, all of them are in the same phase. Now, granted, a lot of that time that actually means that we are referring to liquids, but it could also be gases. I will go so far as to say there is a distant possibility it could be solids, but that's not super likely if we're talking about the homogeneous ones. And I kind of like this little picture here, just because it kind of gives you the idea, oh, okay, we've got a flask. It's got more than one item in it. You can kind of see alkenes are mentioned along with hydrogen peroxide as being reactants there on the left-hand side of the flask. And then we see the arrows kind of spraddling apart, going over toward the right-hand side. And it will eventually convert an alkene into an aldehyde, things that we've seen in past chapters in terms of what an alkene is and what an aldehyde is. But it all happens there kind of in the flask. It happens in these sort of liquid mixed phase. So the heterogeneous, okay, sort of opposite. We have different phases. You will often see a catalyst, in this case, be a solid, whereas the reactant usually is a gas or a liquid. And it talks about it, if you read back through some descriptions of how this reaction occurs, they will talk about it as being adsorbed. Note, there's a spelling difference here, okay? Adsorbed and absorbed are not the same thing. And I will steal from my mentor who came up with this description. He is unfortunately deceased. I miss him a great deal. He was a analytical chemist and had a great sense of humor. The way he described it was, adsorb was pie on your face, absorb was pie in your mouth. Because one sticks to the outside, the other is more internalized. So again, I kind of went looking for some pictures to kind of make this a little bit more obvious. If you look at the latter, the lower half of that picture there, you can see the catalyst surface. So basically it's a plate or a solid surface there. And as your reactants come down, stick to it, they're then going to form the intermediate or the transition phase. and then eventually your product is produced. Why would we want something like this? So a traditional, not hybrid, not electric car has in these days a catalytic converter. And the catalytic converter literally does kind of what it says, or the way it's described here, in that you have a solid catalyst. And one of the reasons it costs so much if you have to have your catalytic converter either worked on or replaced is they use nickel, platinum, or sometimes palladium, okay? Also rhodium, okay? Nickel, not so much in your car. Rhodium is more likely for that. But all of those are heavy metals. They're also kind of expensive heavy metals. So kind of the way this works is, since burning of octane, okay, hydrocarbon, has a couple of main products. You have carbon dioxide and hydrogen, or carbon monoxide, nitrogen monoxide, a little sulfur dioxide. All of those things are being produced by combustion. All of those are greenhouse gases, not to mention somewhat toxic. So we want to convert them into things that are less toxic. So take a look there at the carbon monoxide along with a little bit of hydrocarbon. And this tells you that upon the reaction that is catalyzed, you get things that are less toxic. Carbon dioxide and water. Well, obviously, water is not toxic unless you're breathing it. The carbon dioxide, okay, your body obviously creates it, but if there's too much of it in the atmosphere, that causes its own set of problems. If we look at the lower of the two reactions there, NO as well as NO2, we're going to swap an oxygen. And this is going to give you nitrogen gas and oxygen gas. Now, all of this said, catalytic converters are not particularly perfect. This is why when they always tell you that if you're going to start your car and it's in a garage, make sure you open the door before you start your car. Because even though you have a catalytic converter, it's still only going to make these particular reactions go or function a certain amount. It's not a really great system. It's better than nothing at all, but it's still not a really great system. You can still get quite a bit of carbon monoxide that doesn't get catalyzed over into the less toxic substances. Now, the enzyme one, this one is kind of both better and faster, but it's also more specific. So an enzyme, and even if you had only high school biology, you've probably heard about them a little bit, is a biological catalyst. And it is very, very specific. Think of it, if you look kind of at the pictures here, they're kind of like metabolic or biological Pac-Man, that they have a slot that has a particular shape, and the substrate, meaning the thing that's going to react, will either fit in the enzyme or it won't. Okay. If it does fit into the enzyme, it fits into this little spot called the active site. And you get, again, kind of a transition state. Specifically, they refer to it as the enzyme substrate complex. And then your enzyme does its thing and it pops things apart or puts them together, depending upon what kind of an enzyme we're talking about, and goes about its business. And remember, in the terms of all catalysts, gets reused. So note that we can increase our reaction rate huge amounts. So 10 to the 6 all the way up to 10 to the 12th. And sometimes you will see this referred to as the lock and key theory. The idea being that you only have one key for each and every lock. So only one substrate fits with one active site. If I want to be a little bit more truthful about the biochemistry of this, it's a little bit closer to the concept of hand in a glove. So think about, okay, you go to like Walmart or the dollar store and you buy a pair of cheap gloves. So, and they probably say one size fits all, which is limitedly true, meaning that they're probably too big for a child hand, and they're probably not big enough for some people. Like, okay, my son has really long fingers, and he has trouble buying gloves that fit correctly. So there's a limit to how far you can kind of push the idea, but if they're stretchy, there's probably quite a range of adult-sized hands that could fit in a cheap pair of stretchy gloves. So lock and key is one idea, but glove and hand and glove is probably a little bit closer to reality. And the last little bit here, since we've been talking about kinetics, note when the E and the S, the enzyme and substrate, stick together, that's usually pretty fast. It's the phase where the complex then turns into product and gives you back your enzyme that probably controls how fast you can do this. So that's why the K is written above there, because the rate constant is usually more closely tied to the second phase of that particular type of reaction, as opposed to applying it to the first phase. All right, so that gets us all the way through the end of kinetics. Let me pop back open my whiteboard here, and I'm going to get rid of my all right, so just to kind of give you sort of reminders. So homework for kinetics is going to be due Thursday, because remember I said I did not want to make it due basically before your test allotted time was completed, and that went or clicked off last night at midnight, this morning at midnight, however you want to approach that idea. And this gives you a couple more days. Hopefully you've done some work on the kinetic stuff already, but this gives you a couple more days to work on it. Let me find my file for the homework. Which I've probably put it in the wrong folder. I'm like looking at my other folder going, I see my notes, but I don't see my, homework set. Aha, there, found it. Okay, give me a second to go back to the share. All right, so this is your kinetics homework. So the first one gives you some data. Assess the data, write your rate law, and then calculate the rate constant. So there's kind of two parts to that question. The next one, I gave you a rate law, and then I gave you some additional information so that you can calculate the rate. Number 3 is a conceptual question. For number 4, you know that this is a second order reaction. It actually doesn't even matter what the compounds are. It's a decomposition reaction, because it says A gives C and D. And I gave you a rate constant, and I gave you an initial. Find the half-life. For number 5, this one is based upon the idea of activation energy. You could do it by the graphical method, but that's really not exactly what I'm looking for. I suggest that doing it by the slope method is probably more straightforward. Then we have another first order reaction, and this one has 2 halves to it. Now, the first half of this question is more straightforward than the second half. We know it's first order. We know that you're starting with 68 grams, and we want to figure out how long it takes to only have 5 grams left. So think about the way that that needs to work from an equational point of view. Now, the second part has more complexity to it. This time I gave you a time, and if the reaction is stopped at 25 minutes, you're then going to need to find out how much of the products were created. And then I will tip you off in that you are going to need the ideal gas law to finish that question. So part B is supposed to be the harder part of that. All the rest of them are more straightforward and direct applications of things covered in the chapter, but that last part B of the final question there is a little bit nastier. All right, so I'm trying to, there. Okay. So I'm gonna try, especially because I don't have my webcam with me today. I think it's on the bottom of your screen, you should see the little yes, no buttons that allow you to respond, just so that I can make sure everybody has access to the homework. So if you've at least had a look at it and make sure that you can like download it from Canvas, if you could like hit the yes buttons just so that I can kind of keep track of everybody having good access for this, because I know that we've had a couple people have had a little bit of off again, on again access problems. So see if you can find the little yes button and hit them. Can I tell? Can I even see when you do it? My brain is like going, I'm not sure. Oh yeah, okay, I see it from at least one person. So yeah, see if you can find the yes, no. Let me know if you've been having okay success at actually getting the homework and being able to view it. I see a couple of yeses. but I don't have any no's. Truthfully, I'm not actually exactly sure where it displays on your end of the Zoom interface. Okay. I don't know, maybe people are having problems finding it. All right, I'm gonna switch gears then, and we're gonna dive a little bit into equilibrium. I posted the notes for equilibrium this morning, I think. Like I said, my brain, for some reason, my keeping track of things today has like not been particularly great. I know that I did post them. I just don't remember exactly when I posted them. So let me trade folders again. I've got everything kind of been trying to keep track of everything that I've made changes to by dumping it into a new folder. Share screen. Oh, that didn't work well. Okay. Why is that not showing up? Share screen. Ah, there they are. Okay. All right. So on to the next chapter. This one is about general equilibrium. And in fact, a substantial portion of the remainder of the semester is based on variations on equilibrium. One of the things that makes this different from a lot of the things that we have dealt with before is we've been kind of treating reactions as if they were one way. You start at the beginning, you have reactants, the reaction goes, you get products, end of story. In fact, this is sometimes not true. There are some reactions that go in both directions. Now, once you get it going and you kind of leave it be and you're not changing anything dramatically while it's doing its thing, you will get to this state that they refer to as chemical equilibrium. And it's a little bit deceptive because we describe it as a state where the concentration of both the reactants and the products remain constant. Okay. No observable changes doesn't really mean no changes. And I dislike the fact that I can't make my arrows go the way I would like them to in Microsoft Word. And you see here, I have reactants and products, and it looks like I have this really, really long equal sign in between. So let me hop back over to the whiteboard and show you a little bit more how it's sort of supposed to look in terms of drawing your reactant arrows. This is how they usually draw them, or actually a lot of books will draw it this way. Note, I have two arrows that kind of look unfinished, and the one on top is missing the bottom half of the arrow point, and then the one on the bottom is missing the top edge of its arrow point. So you will often see reversible or equilibrium style reactions written with this particular kind of notation. Now, unfortunately, because a lot of the things that I type are dependent upon me using Microsoft Word, they kind of just look like a long equals sign, because that's about as close as I can easily get to make this work. So again, trying to come up with good analogies. So what if you have a sink that doesn't have a super speedy drain, and you turn on the water fairly full blast, and you get a certain amount of water sort of building up in the sink, but after a point, you're kind of reaching this point where the amount that's going down the drain is roughly equal to the amount that's coming from the faucet. And it doesn't change in terms of the depth. That's kind of what's happening here in terms of what's going forward and what's going backward eventually reach this point where it's kind of both happening equally as you go. And I picked on a reaction that's a weak acid, hydrofluoric acid. And if you have hydrofluoric acid reacting with water, this is actually a reversible reaction. If you read it in the traditional direction, you have HF and H2O behaving as reactants, making H3O plus and F minus as your products. But because it is a reversible reaction, if I go back in the other direction, I can also treat my H3O plus and my fluoride as if they were reactants. And I like this graph because it kind of shows you something that looks like a little bit like two overlapping kinetics graphs. When we looked at kinetics at the beginning of the chapter, we saw a curve that looks a great deal like the blue one here that's labeled reactants. At the beginning of the reaction, you have a lot of reactants, and it rather swiftly curves downward, and then it kind of flattens out. Now, when we were dealing strictly with kinetics, we had it somewhat asymptotically approach the lower axis there. It didn't quite exactly reach zero, but it got close to zero if you gave it enough time. If we overlap that with the production of the products, note your products start at basically none. And as you give it time, they get higher and higher, but it kind of plateaus out. And if you look at the right-hand edge there of this graph, you see this area where the red line for products and the blue line for reactants basically are both flattened. This is when you are in the equilibrium state. Now, when we talked about vapor pressure from from a couple of previous chapters is actually a physical equilibrium, such that if we look here at liquid water and gaseous water, and perhaps assuming that we have a flask with a cork in the top of it, and you leave the water sit there for a while at a particular temperature, eventually you get to this point where you have exactly the same amount of water going up from the liquid phase to the gaseous phase as the amount that's coming from the gaseous back down to the liquid. However, also a lot of the things we deal with in this chapter and on into the next chapter have more chemical equilibrium going for them than physical. We're going to kind of give this a generic basis as kind of a place to start. So if you have two things on the left, we're going to call them A and B. Think of the lowercase a and b as your coefficients. And then you make C and D. Again, think of the lowercase ones as your coefficients. We can write an equilibrium expression. Now, unlike the rate laws that we've been dealing with in the past chapter, this one actually takes into account some of your product information. And although it's not super obvious, they will often use a uppercase K as your constant if they are talking about equilibrium versus the lowercase k that we saw when we were dealing with rate laws. So we've got products over reactants. And I know that sounds a little bit backwards, but that's the way the setup works. And another slight benefit to the equilibrium idea versus the rate law idea is we can make some assumptions about coefficients and their exponents. So all those little lowercase letters, A through D, can be utilized as exponents when we write an equilibrium expression. So I started with one here that has 2 and 2. We also need to be aware that the constant, kind of like rates, changes with temperature. If you happen to look up an equilibrium constant for a particular reaction, a lot of times it will tell you, well, this is only the value at 20 Celsius, or this is only the value at 25 Celsius, or something like that, because your equilibrium constants will change with your temperatures. So back to my NO and O3. Swap an oxygen. That way I now get NO2 and O2. And I'm going to write it in my equilibrium expression. Make sure you put the things that are on the right-hand side on the top. Make sure you put the things that are on the left-hand side on the bottom. And because when I look at my original reaction there, all of them have the implied 1. I have no other exponents. I have no squareds or cubes or anything like that. How big the number of your K is also tells you another piece of information. It will tell you whether the reaction favors products or reactants. Okay, favors is kind of an odd term, and yet it's a typical term that's used by textbooks. If you are favoring products, it means you get a lot of products, but there's a little bit of reactants left over, because this is an equilibrium situation. You're never going to go completely and entirely from left to right and have no reactants left over. So the ballparks that are usually used by most textbooks is if your K value is 10 or greater. This is a way to tell you that the products are favored. I switched reactions here. This one still has NO in it, but it's a different reaction. I've got 2 NOs and an oxygen molecule and they all glue together, and I get 2 NO2s. If my K value is 200, well, 200 is bigger than 10. This means when it actually reaches equilibrium, I will have a situation where I have lots of NO2, but I still have a little bit of NO and O2. Probably not much, but a small amount does still exist. How about the opposite end of this? If my K value is 0.1 or less, sometimes you have really small K values, you have reactants favored. Now, chlorine gas, being a diatomic molecule, really hates to fall apart. You can coerce it a little bit, but most of the time it stays as Cl2 and only rarely becomes two separate atoms of Cl. Look at your K value. 1.4 times 10 to the negative 38. So because it is so small, I'm going to get probably 99.99% Cl2 at equilibrium and a very small amount of separate Cls at equilibrium. Well, note, there's kind of a gap between these numbers. First I said bigger than 10. The other one says 0.1 or less. Well, there's this gap in the middle, okay? If you are between 0.1 and 10, the best you can say is that you will have some of both. The how much is going to involve math. Now we're going to revisit some of the words from the previous chapter and actually from other previous chapters. Homogeneous. Most of the time when we are talking about equilibrium, we make certain assumptions. We make assumptions that all the things on both sides, both reactant side and product side probably, are in the same state. Usually it's a gas or liquid/aqueous. Solid is a different situation. We'll come back to that. You will also kind of hang on to the square brackets that we saw in the rate laws. So if you see square brackets, we are going to assume that your concentration is in molarity, moles per liter. And I happen to like the subscript of C. I think your textbook, even though it mentions it, doesn't tend to use it a great deal. I kind of hung on to it from some previous textbooks that I've used because I find that the differential is a little bit better to wrap your brain around. So if we're talking about concentration equilibrium, we're going to call it a Kc. If you're dealing with gases, we're going to call it a Kp. And instead of concentration in molarity, we're going to deal with pressures, atmospheres, millimeters mercury, torrs, pascals, something that is a gaseous pressure. So let me show you the two different ways here to write these ways of expressing your equilibrium. So this is a gaseous reaction. We've got NO and O2, and it makes two NO2s. everything's gas. If I want to write it as an equilibrium expression based on concentrations, still products over reactants, pay attention to your coefficients. I have a 2 out in front of my NO, and I have a 2 in front of my NO2. So they become the squareds in this. But my square brackets mean that this particular K value, my Kc value, is based upon molarity. Now I can write the same equation with a little bit of a variant. If I want to not use molarity, if I want to use pressures, you will usually see this written as a capital letter P with the molecule being written as a subscript. So on the top here, I have P of NO2 squared. The squared is still there. It's just instead of the square brackets, I have capital P's. On the bottom, I've got P of NO squared and P of O2. Again, we're not seeing any square brackets. We're seeing the same molecules, but different notation. Most of the time, the number value for Kc and the number value for Kp are not the same number. You can convert. Now there's two different ways to do this, although we don't usually use the left-hand version. You will see it referenced, P equals CRT. That's kind of hard to deal with because you need some constants that you may or may not have available. The right-hand one, Kp equals Kc in parentheses, 0.0821, because remember, atmospheres is a potential pressure, T, temperature in Kelvin, and note my exponent is delta N. Delta N is what is referred to as your difference in exponents, products minus reactants. Now, sometimes you have a delta N of 0. You have, for instance, 2 things on the left and 2 things on the right. In that case, your Kp and your Kc will be the same. Sometimes they are, sometimes they aren't. So I decided to start with the more straightforward one and then digress to one that isn't. If I have a water molecule and a carbon dioxide, they become hydrogen gas and CO2. And I gave you concentration values for the Kc. So I put all my numbers in where my molecules are given. We have H2 and CO2 on the top. We have water and CO on the bottom. Put in the values that are provided. Crunch all your numbers. My Kc is actually pretty small. So one of the things that I can say about that is that my Kc probably indicates that I will have at equilibrium lots of reactants and not a lot of products. I can even kind of tell that from the numbers. Since my H2 and my CO2 are products, and they are, especially the H2 is a smaller number value than anything on the left-hand side, I kind of already have that idea being put in force. And then it gets reinforced by the time you do the number crunching there. What about COCl2 falling apart into two molecules? In this case, my Kp and my Kc will not be the same because my delta N is not 0. I have 2 products minus 1 reactant. So my delta N is 1. If I know that my Kc value, or yeah, blah, blah, blah. If I know that my Kc value is 4.63 times 10 to the negative third at 800 Kelvin, put it into your formula. Put in your Kc, your R value, 0.0821 does not change. Put in your temperature. I have an exponent of 1, and my K value is 0.304. So note, there's a fairly big difference between my Kp and my Kc there. It is also possible to have a negative value for your delta N. They won't always end up being positive values. You could have an exponent of to the negative 2, okay? So basically that's the same as putting a number over something squared. So make sure you know how to do this on your calculator. Chances are most versions of calculator will provide you with the ability to do something known as y to the x as a way of creating exponents that are not necessarily straightforward or maybe negative. All right, and that's about as deep as I am going to go into equilibrium tonight. On Thursday, we will head in the direction of the ICE method and how to figure out concentrations of all molecules in a reaction at equilibrium. And you get to re-embrace the magic of the quadratic formula. Negative B, or actually, I should say B squared. No, actually, I did it right the first time. Negative B plus or minus square root of B squared minus 4AC all over 2A. Like I said, quadratic formula, which is an algebra tactic. So that is something that is going to pop up here in this chapter. Questions about the tail end of kinetics or any of the equilibrium stuff we have covered so far? Some of you I will see tomorrow night in lab. I am still working on the instructions that go with the rate law lab, which is one of the dry labs. I put up some information, but it is far from complete. There is a video that I stole from somebody else, YouTube, that I like the visuals for, although the reaction version that they're using for the rate law is not exactly the same as the one that we are utilizing from your lab book. And I will be giving you some data to crunch. And once I finish the instructions, there will be more detailed instructions on how to do the math. This is a somewhat involved lab from a math point of view, in that it involves doing some dilutions, doing some rates, doing some natural logs, and 2 graphs, of which the slope is an important key factor. So it's a somewhat involved lab from the math end of things. And like I said, I've only put up some of the information. There is more coming. I've been kind of juggling a little bit of everything right at the moment, trying to keep up with lecture stuff as well as lab stuff. And remember that we are heading towards spring break. So the molar mass of a solid lab, which some people are doing this week and other people are doing next week, both of those end up being due after spring break, which I think I put in the due dates as something like the 17th of March. So those are sort of upcoming things to keep an eye on. Questions? Otherwise, I will see some of you tomorrow, and hopefully I will have my webcam on Thursday for lecture. Bye.